Welcome back to Solids and Liquids. Today we're going to talk about types of solids. And so let's go ahead and go. First up is network covalent. So network covalent has this very familiar word, which is covalent. And so that means the same thing as we've already said that it means. That is covalent bonds. And so network covalent is a network of covalent bonds. So for example, diamond. Diamond, the chemical formula for diamond is C, as in carbon, plain carbon. And so there's a C here and a C there, and there's just a whole bunch of carbons. And then they're all bonded to each other with covalent bonds. And it's a network of covalent bonds. And so if we erase that, you can actually get to the real picture of what it looks like in a three-dimensional structure. Well, at least kind of. Graphite and carbon actually have the exact same chemical formula. The chemical formula for graphite is also C, just the carbons are covalently bonded in a different way. And then if you have silicon dioxide, these little black ones are silicon, these little red ones are oxygen. And it's just a network of covalently bonded silicons and oxygens. And so if you count up in a sample of silicon dioxide how many silicons and how many oxygens, whoa, I wrote O2. That's just O, there will always be twice as many oxygens as there are silicons. The reason why it's not O2 is because it's not oxygen molecular by itself. Instead, it's oxygen bonded to silicon, and so it has a friend, it doesn't need to be its own friend. Let's write all that down. The particles occupying lattice sites, that is the things that are on the corners of a solid, if it were a solid. And in this case, it is atoms. And so in silicon dioxide, it's atoms of silicon and atoms of oxygen. In carbon, diamond, or graphite, it's atoms of carbon. So the attractive forces to be broken are covalent bonds. This is not the same thing as the intermolecular forces, like say between two water molecules, where you were not breaking the bond between H and O. Instead, it's as if all of the water molecules were covalently bonded to every other water molecule. So if you wanted to break one apart, you would actually have to break a bond, not just an intermolecular force. So the properties of these, since you have to break covalent bonds to do anything with it, is that they're really tough to break. So typically they're solids at room temperature. They're usually very hard. They have a high melting point and boiling point. Generally, they're insoluble in most solvents. And finally, they are typically insulators. Typically, they're insulators. There are some that are conductors or even semiconductors, but we'll get into that a little bit later. So, some examples of this are typically your metalloids, that'd be carbon or silicon or germanium or boron, or molecules, what we would think of as molecules with metalloids in them, such as silicon carbide or boron nitride or silicon dioxide. Now, with network covalent only, I want you to memorize these 7 things. These are the only ones that you will ever see, not the only ones that exist, but the only ones that you will ever see as examples of network covalent. So if you see these 7 things, the atoms, carbon, silicon, germanium, or boron, or the molecules, silicon carbide, silicon dioxide, or boron nitride, just automatically think network covalent. Next we have ionic bonding. Now we've already talked about ionic bonding in the intermolecular forces section, and technically the ion-ion force that we had talked about earlier is not really an intermolecular force because there's really no molecules, so you can't be intermolecular. So it's interatom force maybe. So we have the Na pluses, which are the small purple ones, and we have the Cl minuses, which are, let's try the larger green ones. And since the sodiums give their electrons away to the chlorines, the sodiums are positive, the chlorines are negative, Chlorines are larger because they have an extra energy level. And so now we've got positives and negatives all sitting next to each other and attracted to each other because of their opposite charges. So if you took a salt crystal and looked at it under an electron microscope, you'd have a huge lattice of interlocking positives and negative charges. So this is your ion-ion force that we had talked about earlier in intermolecular forces, even though it's technically not an intermolecular force. So the particles occupying a lattice site, or the corners of an ion-ion thing, or an ionic solid, are of course ions. They are cations and anions. Remember, cations are the positive ones because they have a little t, and anions are a negative ion because they're negative. So the attractive forces to be broken, in order to get an ionic solid apart from itself, you have to get apart the ion-ion attraction. You have to get apart the ion-ion attraction, or the electrostatic attraction between a positive and negative ion. So properties of ionic solids is that they are typically solids, because opposite charges hold together pretty well. Let me get that a little bit prettier. And they are also typically have a high melting and boiling point. They dissolve in water. Because water is polar and it has those opposite charges, and the ions have the opposite charges, then they can break apart in the water. They're also a good conductor only when liquid, as in molted or melted, or when dissolved. If they're a solid, they would be an insulator, not a conductor. So for example, if I tried to conduct electricity with just a giant jar of salt, it wouldn't work. But if I poured water into the salt, then it would conduct electricity. So some examples of that would be salt, NaCl. Really pick your own favorite ionic compound here. Something with a polyatomic ion like potassium nitrate or ammonium chloride. Or, I don't know, calcium fluoride. Really any ionic compound is an ion. Next we have metallic bonding. And so metallic bonding is obviously the bonding between metals. And so in a metal, like let's just say Na, because I've got that on the brain from the ions, Na plus would lose an electron. And so let's just say you had pure sodium, you hadn't mixed it with chlorine. And so that plus means an electron is being lost. And if that electron's being lost, where's it going if there's no chlorine? So let's pretend over here that this picture, these pluses are all Na pluses. And it loses an electron. So that electron just kind of hangs out somewhere in between the metals. So there's a whole bunch of Na plus ions and a whole bunch of electrons just kind of floating around. And so then those electrons that float around really do move completely randomly. Just, float around here, maybe some of that, and let's do a little bit of, whoa, where are we going? And so since those electrons can move very easily, it actually conducts electricity very easily, because conducting electricity is just conducting electrons. So the particles occupying the lattice sites of a metal are positive ions. Not positive and negative, because the negative ions would be the nonmetal, like in, say, salt, but just the positive ions, just Na plus or Cu plus 2 or Ag plus, something along those lines. So if you want to break a metal, let's say we want to take a metal disc and split it in half, we would have to break the attraction between positive ions and the electron cloud. We would have to break the attraction between positive ions and the electron cloud. The electron's negative, the ions are positive because they've lost their electrons, and so those are the forces you're going to have to break. So properties Now, metals tend to vary. Some metals are soft like butter, some metals are liquid like mercury, and some metals are really hard like gold or platinum. So the properties really do vary a lot, but they tend to be solid at room temperature. They tend to be shiny, have a metallic luster. They tend to be insoluble in most liquids. They have a wide range of hardness. Whereas ionic and network covalent are always hard. Metals could be mercury or sodium or gold. And they also have a wide range of melting points and boiling points. Generally, they're high, but there is a huge range. They are good conductors. And they're good conductors when they're molten, just like ionic solids are. Well, ionic liquids, I suppose. But they're also good conductors when solid, which is what separates them from ionic compounds. One way you can tell. So an example, pick your favorite metal here. I like sodium. I also like gold and silver. Mercury's kind of cool. So's calcium. Aluminum really helps me out with storing my food. Just whatever metal you tend to like. Next we have molecular covalent. So again, this is covalent bonds, just like network covalent was. But the difference is we're making molecules that are held together with covalent bonds, not a giant network of covalent bonds. So this is what we'd already been talking about with the intermolecular forces earlier. Like let's say I've got a water molecule. So this is a molecule, and this is another molecule of water, and they're held together with covalent bonds. And the intermolecular forces are the forces between the hydrogen and the oxygen of two different water molecules. So they're covalent bonds, but held together with intermolecular forces. These are the IMFs. And so I've got a whole bunch of pictures of different types of molecular covalent bonds. We've got the HCl, where the negative part of the Cl is attracted to the positive part of another HCl. We can pretend like this one's HCl. Who knows what atom it really is? The negative is attracted to the positive is attracted to the negative. With another HCl, the positive is attracted to the negative. Here we have a little bit more of a complicated structure. Notice the hydrogen bonding going on, where the hydrogen is bonded to oxygen in one compound and attracted to oxygen in another. Hydrogen bonded to oxygen, attracted to another oxygen. So here the particles occupying lattice sites are atoms or molecules. Could be either atoms or molecules, but the forces that we're breaking are not the covalent bonds, but the intermolecular forces. These are the same intermolecular forces we had talked about before. So that would be the hydrogen bonding. That's hydrogen with NO or F attracted to NO or F in another molecule. That's dipole-dipole. Two polar molecules attracted to each other. Or even London dispersion forces, which are two nonpolar molecules or two nonpolar atoms that are attracted to each other. So the properties of these are much weaker compared to the others. They tend to be liquids or gases at room temperature. If they're going to be a solid, it'll be a soft solid like butter. So it'll be soft and waxy if it's a solid. They can dissolve in water and they can not dissolve in water depending on what type they are. So if it's a polar molecule, it dissolves in water. If it's a nonpolar molecule, it will dissolve in something else that is nonpolar. I'm just going to write oil because that's a common one. Let's see. They have low melting points and boiling points. Really, really low melting points and boiling points if they're a gas at room temperature. And they do not conduct electricity. as a solid or a liquid. Wow, does that look like solid? Let's try that again. So some examples of these are examples of virtually everything that we had previously talked about. I'm not happy with that D. Let's try it over. So that could be water. That could be HCl. That could be something that's nonpolar, let's say CH4, or neon, argon, krypton, any of the noble gases, fluorine, or oxygen, or any of the diatomic molecules. Really anything that is a molecule that is separate from another molecule. So let's kind of look at this as a big picture way. If we have a solid, it can be made out of molecules, or ions, or atoms. If that solid is made out of molecules, that is, the composite units are molecules, that's what's at the corners of a solid, then they'll tend to have low melting points. These are going to be polar things or non-polar things within the molecule held with covalent bonds, but between the molecules held with intermolecular forces. If the corners of the solid are ions, so this is ionic bonding, they're going to tend to have high melting points. These are ion-ion forces, like table salt, or Epsom salts, or really any kind of salts, ocean salt. And if the corners of a solid are atoms, so the composite units are atoms, well, it can go lots of different directions. They could be non-bonding atoms, as in non-polar, held together by London dispersion forces, so these are like solid xenon. They could be metal atoms, so held together by metallic bonds, and they have variable melting points, but gold or silver or mercury. Or they could be held together by covalent bonds, and this is your network covalent with high melting points such as quartz. Which leads us into what is the relative strength of everything that we have discussed at this point. So I'm going to start with network covalent. This tends to be the very strongest, the very hardest to break. Network covalent bonds, because you have to break the actual covalent bonds to break apart the thing, which is why diamonds are so hard. So then after network covalent, we have ionic, which you might think of as ion-ion forces or ionic bonding, however you want to think about it. Then we have metallic. Now remember that metallic has a large range. Some metals are really hard and some metals are really soft, and it kind of just depends on where their electrons are and what their valence electrons are doing. So metals can be a big range, but they tend to be strong just underneath ionic. Then we have intermolecular forces. And within the intermolecular forces, we have the ion dipole. Then we have the hydrogen bonding. Next is the dipole-dipole. The ion-induced dipole. The dipole-induced dipole. And finally, the induced dipole, otherwise known as London dispersion forces. So remember that dipole-dipole, this is a polar compound, a pure polar compound. Hydrogen bonding is a pure polar compound. And London dispersion forces are pure nonpolar compounds, molecules or atoms. The other ones are mixtures. So dipole-induced dipole is a mixture of polar, nonpolar. Ion-induced dipole is a mixture of ionic and nonpolar. ion dipole is a mixture of ionic and polar. So remember the difference between pure substances and mixtures. And that's the general strength of those. Go back to video 1 if you want to know more about those different types of IMF. And that's it for different types of solids. Join me next time and we'll talk about semiconductors and types of alloys.